Okay, you're in calculus class and you're looking at limits, and maybe you're having a little bit of trouble, so we're going to not breeze through, but go over a couple easier topics with limits, and then maybe look at a couple harder ones here. So, basic idea is you're coming across things that look like this, the limit. X goes to some number, I'm just making this up as we go along here. X squared minus 4. Okay, now the easiest way to think about these guys is graphically. To answer this one, actually just plug in. You plug in 3, and you get 3 squared is 9 minus 4. The answer is 5. Okay? But we need to talk about why. Why is the answer 5? Why is it just plug it in? That's so easy. What's the point of all this crap in the first place? So, where's the line? Here we go. Let's take a look at what x squared minus 4 looks like. Because the reason you can just plug in here is actually because x squared minus 4 has a special feature. So x squared minus 4 is a parabola. I'm drawing the best I can here. Looks something along these lines. Looks pretty good, Mr. Smith. Thanks, Mr. Smith. Okay. The zeros are at 2 and negative 2. This is negative 4, and this doesn't really matter. I'm just helping you get a picture of what the graph looks like. And we want to know what's happening when x gets super close to 3. That's exactly what this limit means. X is getting close to 3. What is the height, the y value, on x squared minus 4? Well, 3 is out here somewhere, so 3. Thank you, I've asked. And you can see the point is up here, and we're saying that's going to be 5. So 5. So like 1, 2, 3, 4, 5. There you go. And at 3, the function equals 5. That's the point there. Okay? Now, generally, actually, well, all the time, when you're doing a limit, you don't really care what's happening at 3. Yeah, the answer is 5 when you put 3. That's great, but that's not why the limit equals 5. The limit equals 5 because for values around 3, for x values around 3, so if you're down in this interval, or this interval, and you're moving closer to 3, the graph up here is moving closer to the point that's there. Like that. Okay, and the closer you bring in these x values to 3, the closer you get to 3. Imagine me zooming all the way in here, and we're talking about like 2.999999, just going on forever. The closer this graph up here gets to 5. Now, what happens when you get to 3? Well, the graph gets to 5. That doesn't have to happen. Okay, we're worried about what is the function closing in on as x closes in on 3. Now, I'm going to show you an example of one where you can't just plug in, and we'll look at the graph on that one too. But I guess in general, the rule is if you can plug in and it's a nice function and you just get a number back, that's your answer. There's really nothing to it. Okay, and we'll talk about exactly the differences here for when you can't do that. But let's look at, I'm just going to make up a different graph. Okay, let's look at, so here's our coordinate axis. Let's look at a graph like this. Okay. Now usually when you're doing a limit, you're going to be concerned with points that are a little bit more difficult to deal with. Like, again, we go back here. This whole thing is continuous. There's no holes. Nothing crazy is going on. So anytime you want to find the limit, just plug it in. Like, I mean, we could change this question to, what's the limit as x goes to, it doesn't matter, negative 1 of x squared minus 4. We just plug in negative 1. You get 1 minus 4, negative 3. And that's right here. Negative 1, right there, negative 3. And we're allowed to just plug in. Okay? So let's go back to this other graph. Over here, let's say this is, again, I'm just choosing random numbers here. This doesn't really matter. This is 4, and let's say the height it's at is 3. So the question you're going to be seeing here is limit x goes to 4 of f of x equals what? Okay, so x is getting super close to 4. What's f of x getting super close to? Well, the first thing that you should try, like I said, for number 1, you just plug in. So the first thing you're going to try here is you're going to plug in f of 4. The problem with f of 4 is it's undefined. There's no point there. There's a hole there. So graphically you can see what's going on, but if you didn't have a graph of this thing, you just had like an actual explicit function, which we'll look at next, you wouldn't be able to do this. You'd have to do some more extra work. But anyway, the thing's undefined here. But you can see, even though there's no point there, as x moves into 4, right before it gets to 4, again, I don't care what happens when it gets to 4. I care what happens as it gets super close to 4, but not when it turns into 4. This graph is moving super close to where that hole is, 3. And the closer I get to 4, the closer x values I pick to 4, the closer these y values are going to be to this hole here, because the hole only exists at 4. So if you plug in, again, like 3.9999999 or 4.000001, you're going to get values back, and they're going to be super close to this hole, which is at 3. So this limit actually equals 3. And that's really not a problem. It's just what is the function getting close to as x gets close to 4. It doesn't matter what happens when x gets to 4. It matters what happens as x gets super close to 4, but not when it equals it. Okay, so let's look at an example where you'd actually get a function where this would happen. So let's say you're in calculus class, totally prepared. Your teacher gives you this guy. Limit x goes to 3 of x squared minus 9 over x minus 3. Alright, first thing you're going to do is try to plug in 3. Always do that. So you try to plug in 3 and you're going to get 0 over 0. And usually that's going to happen. But if you don't get 0 over 0, you don't have to do all the work that we're about to do. If you get just a number, then that's your answer. But anyway, in this case we get 0 over 0, which means this fraction here has a special name. It's called indeterminate. Indeterminate. There we go. Super sloppy. Okay, and it's indeterminate because when you get 0 over 0 in a limit, you don't know what's happening there. Like if we go back here, there could be a hole. Let's just draw a couple examples of what could be happening when you get 0 over 0. There could be an asymptote, so we could have this going on at 3. So let's say that's 3. That could be happening if we get 0 over 0. It could just be a hole, so we could have a graph like this, like we just had. So there's a hole at 3. There could be a jump. Your graph could be going like this at 3. Okay, so there's a bunch of possibilities here. And now the rule is this limit is only going to work out. It's only going to exist if the graph just has a hole, like this one right here in the middle. If there's a hole, then the limit's going to exist, because even though there's no point at 3, the graph is getting super close to that hole on each side. That's what happened back here. We got super close to that hole, which is at 3. So the limit existed. And the way you're going to know is you're going to do a little bit of algebra. So let's get all this junk out of here. Goodbye, junk. We can get rid of indeterminate as well. There we go. Okay. Let's talk about what this function looks like. X squared minus 9 over x minus 3 before we do the limit. So x squared minus 9 is really the same thing as x minus 3 times x plus 3, because that's what it factors into on top, over x minus 3. And since this is all multiplication up top, these things are going to cancel, and this thing just equals x plus 3. So this graph, x squared minus 9 over x minus 3, is exactly the same thing as x plus 3, except for at one point, 3. Because when you plug 3 into this thing, you get 0 over 0, which is an undefined number. So our original graph is not defined at 3, where this thing is. So usually you put like x cannot equal 3. Okay. Now this thing and this thing are the same exact thing. Well, x plus 3 is just a line, which means this guy up here, this fraction, even though it looks a little scarier, is just a line. And the exact line is x plus 3. So we've got a y-intercept of 3. I'll try and draw this the best I can here. Something like that. Looks like this guy. Okay? But x cannot equal 3, because at 3 we get 0 over 0. So there's just a hole there. So at positive 3, there's a hole there. Like that. But we don't care about what's happening at 3. We care what's happening around 3. So this is the beauty of how this all works. Since x plus 3 and this guy up here are the same exact thing, they must be approaching the same exact number. Now, x plus 3 when x equals 3 is 6. Okay, so the limit as x goes to 3 of x plus 3 is 6. Because x plus 3 is a continuous function. At 3 it equals 6, so really this hole would just be filled in. At 3 this thing equals 6, and since it's continuous, it cannot get to 6 without approaching 6, if that makes sense. Again, we got this line. This is what x plus 3 looks like. Well, if at 3 the thing equals 6, as x approaches 3 from both sides, well, this graph has to approach that point. It's got to. It's continuous. This thing, we didn't know what was happening. We got 0 over 0, so we can't visualize what's going on there. That's why we had to do this extra work and break it down a little bit. But this function here is 6 at 3, so as x approaches 3, the function y must approach 6. It's got to. And since we don't care about, up here on this original one, we don't care what happens at 3, we just care what happens as x gets close to 3, since x squared minus 9 over x minus 3 is exactly the same thing as x plus 3 everywhere except for 3, then this thing must also be approaching 6, which is why there's a hole there. Okay, and you can see that, like, if you bring x super close to 3 on this guy, well, the graph is going to move in towards this hole. Now, what happens as it gets to 3? Who cares? Not me. It just gets super, super, super close to 6. When it gets to 3, it's undefined, doesn't matter. And the way we know that is this function, same thing. Okay, so the trick is, when you have an algebraic function, your job is to simplify it down so that you can plug in the number and get an answer back. Because as long as you follow the correct algebra, if you simplify down a function to get a new function, and you did all your algebra right, like here all I do is factored and canceled, well then your old function and your new function are the same exact thing, except for the point you canceled out, which means there's a hole there, which you should have learned in pre-calculus. If common factors cancel out, then there's a hole wherever those factors equal 0. And if there's a hole, then there's a limit. Okay, that's the basic idea. Now, there's a bunch of different ways we can do limits here. We can do with square roots and fractions, all kinds of crazy stuff with trig, and we'll look at those in the next video. But just for the main idea, remember, all we care about is what's our graph getting close to as x gets close to that number. That's all. We don't care what's happening at that point. We care what's happening around that point. And the main thing here is when you got an algebraic function and you get 0 over 0, your job is to simplify it down until you can plug in that number here. We plugged in x minus 3, or I'm sorry, x equals 3. That's what we want. So we can plug in 3 and get an answer, because if this thing equals 6 at 3, I know I said this, I'm going to repeat myself. If x plus 3 equals 6 when x is 3, then it must be approaching 6 as x approaches 3. That's why the limit equals 6. Not because it's equal to 6, but because it's approaching 6. And if x plus 3 is approaching 6, this function up here must be approaching 6 because it's the same exact thing except for at 3, and we don't care what's happening at 3, we care what's happening as we approach 3. Alright, that was a mouthful. We'll do a lot more examples in the next one. I hope that makes sense. If not, shoot me an email, ask me in class.